In our previous couple of problems, we worked multi-node problems where you have to start at a given node and then you have to work at a proper sequence to get other unknowns. And we're applying the principles of particle equilibrium one node at a time. In these particular examples, all of the links are cables and they're all in tension. But you could easily imagine that we could replace the cables with links, and depending on how we load it, these all could be in compression, they could all be in tension, or they could be some mix of tension and compression. And you might suspect where I'm heading with this is we're working our way toward truss analysis, actually. But let's work this problem first. So this particular problem first, there's 1, 2, 3, 4 links. They're all pivoting. Here we're pushing on it with a 100-pound force P. And if we're pushing on this guy, then these guys are in compression, and then these guys are in compression. Every link is in compression. If I actually turned P around and pulled on this guy, then this would be in tension, this would be in tension, this would be tension, this would be tension, and I could replace all of these guys with cables. And so I could do a cable here, a cable here, a cable here, a cable here, ground, 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 and then I'm pulling on P. And these would all be in tension. But this is the reverse of it where I'm pushing. So I want to analyze all of the forces in all of these links. I can't start at D because I have 3 unknowns at D and no known. But if I start at B, I have a force here and I have 2 unknowns. So if you draw a free body diagram of B, I draw the 100-pound guy going down. And let me just show you how I do this. So if you look at B, and this is 100 at a 3, 4, 5 slope. This is 3 over 4. This is 100. You know that because these are links that are free to rotate, then they develop a force along their axis. They're what we call 2 force members. And so I know that they have a line of action, but notice I haven't drawn arrows yet. And I can label this. I can label this F, B, C. I can label this F, B, D. But I haven't given them arrows yet. So if I sum forces in mentally in the vertical direction at joint B, because this guy's acting downward, that pretty much tells you that FBD has to push upward. Because of these 2 unknowns, he's the only one with a Y component. So he has to push upward to keep pin B in Y equilibrium. Once you figure that out, then you realize, okay, this guy has to be this direction. Because if you sum forces in the X direction, he doesn't go this way, he goes, it's this way. So this is 100 at 3, 4, line of action. Yeah, that's why you do it. And so this is F, B, C, this is F, B, D, and if this is X and this is Y, if you start by mentally summing forces in the X direction, it's indeterminate because both of these guys have X components. But if you mentally sum forces in the Y direction, BC does not have a Y component. And so it's clear that FBD has to act upward on pin B for B to be in Y equilibrium. Once you get this guy this direction and this direction, then if you mentally sum forces in the X direction, it's clear that FBC has to act to the right for this pin to be in X equilibrium. That's how you do it, not this way, this way. So that's how I approach a free body diagram like this. Once you have that free body diagram of B, you can solve it. For some forces in the y direction, I have 12/13 FBD minus 4/5 of 100. This has no y component. FBD is 86.67 pounds. He's pushing, and so he's in compression. For some forces in the x direction, you got FBC minus 3/5 of 100 minus 5/13 of FBD, and I get FBC is 93.3 pounds, which is actually pretty much what we got over here on this previous problem. So that's joint B. Once I get FBD is equal to 86.67 and he's pushing, now I can draw the joint D and I can put that member as pushing on D with 86.67. And then it's pretty clear, this is horizontal and vertical. So it's, if you sum forces in mentally in the X direction, FDE has to push and FDF has to go up. If you sum forces X and Y, you get FDE is 33.3 pounds and FDF is 80. Once you get to this point, you can double check it. You can take the overall free body diagram. This is horizontal, this is horizontal. The vertical component here is 80. This guy's vertical, and so he has to be 80. And so that's as we expected. And we can at least check that.